Welcome everyone to this week's collective learning meeting. Please remember to mute your microphones unless you want to ask a question. The presenters prefer that you hold your questions until the end unless you are confused and need clarification. Please feel free to use the chat box. If you type a question there, Raafat can address it. Our presenters today are Ken Cooper and Raafat Zaini. Ken Cooper has been a leader in the field of system dynamics for over 40 years, originally studying under Jay Forrester. He is a two-time Edelman Laureate. And Raafat is a research scientist at the Social Science and Policy Studies Department at WPI and has been working has over 20 years of industry experience. Okay, please take it away, Ken.
Thanks, Christine. So I have the privilege of doing the presenting, or most of the presenting today, but I want to make clear that Raafat really has done the heavy lifting in this work. But again, thanks for the opportunity to be here. We are really happy to have the chance to talk about this this work in progress that Raafat and I have been working on for a few months, part-time. What we're going to do is to go through a discussion of a model that we have designed and built that addresses how the phenomenon of cytokine storms occurs. It is we've undertaken this on our own just because we were very interested in the subject. We're ideally going to find paths to and perhaps through this venue for referrals to subject matter experts that can help us going forward in correcting and improving what we've done. So for this, I'm going to offer a brief background on cytokines. Understanding that neither Raafat nor I is a scientist in the medical world, but just very briefly for those who don't have a familiarity with it, cytokines, as it says on the word slide here, are very strong chemicals that the immune system uses and releases. Various cells in the immune system release these chemicals that are intended, whose function is, there are actually multiple functions, but one of the main ones is to gear up the immune response to be faster and stronger in battling any kind of antigen, and that certainly includes viruses such as COVID-19. This escalation of the immune response is necessary to battle the virus, but it does involve a very crucial balancing process. If there's not enough cytokine-induced activity, well, the virus continues and perhaps worsens. If there's too much cytokine response, then it can become that so-called cytokine storm, in which the immune chemicals themselves damage the lungs, and that is actually what is that immune response of a cytokine storm is actually what is responsible, we've come to learn, for most deaths attributed to COVID. So what we have in the current simulation model is the primary factors include the COVID infected cells, the level of cytokines, level of T cells, memory T cells, and noting that that's a key aspect of the vaccines, as well as a measure of lung damage that's caused both by the virus and the cytokines. These and many other factors interact in the human immune system. This is not a full model of the immune system, but what we see to be the key players in this phenomenon. The immune system as a whole is a really beautifully elegant, complex, feedback-intensive control system, and we will take a glimpse at the Stella produced diagram of the model, and you will see in the lower left corner there the point at which we infect this simulated system with COVID. The numbers of COVID infected cells triggering a cytokine response, triggering the release of and proliferation of T cells, some of which become memory T cells. Those are the ones that will hang on for in the system for a long time to help with any subsequent or future infection. And both of the level of virus and the level of cytokines contribute to lung damage. So what we'll do is to go through a few of the simulation results under different conditions that we've seen so far. In this first scenario that we have here, this is a very mild case of COVID. The plot on this upper right, shown in blue, shows the virus replicating, growing to a level, and then eventually being cleared. And the whole process takes less than 7 days. The cytokines in that time frame rise in response to detecting the virus after a certain delay. It does take the immune system a short time, a day or two, to recognize the presence of the danger in the case of a virus infection, or this one anyway. And then they, after they've done their duty, they decline as the infection clears. Throughout that, there's very minimal lung damage. In this case, it's less than 1% of the lung that's far less that's damaged. So a case of COVID where there are probably symptoms, but not very much and very short-lived. With the cytokine growth, and the viral infection, the cytokines induce a strong T cell response, and the red plot portrays the rise of the number of T cells. Once they've done their job, they die off. Most of them die off, but some of them transition into a state of memory T cells, shown in blue, and they will stay in the body for years, ready, and that's what prepares your body for dealing more quickly with a subsequent infection. And that's specifically what the mRNA vaccines are targeted to produce, not so much antibodies, but the T cells that actually kill virus-infected cells. If we change a few, and we'll talk, excuse me, we'll talk about which factors, but just to illustrate the range of outcomes that we're simulating, just a few input changes to some numerical factors in the model yields, in this case, we're going to look at here, an extremely different outcome. Here, the level of cytokines grows exponentially to the level that certainly qualifies as a storm. and billions of lung cells are damaged, and ultimately that leads to death. The lung cell damage is, in this case, as in many scenarios that we've simulated, caused primarily, not exclusively, but primarily by the cytokine storm, and not as much by the virus. And this plot on the left here demonstrates that. This is the pace of lung damage over the course of those several days. In the blue, the noticeable but modest amount of damage caused by the virus itself, and then on the same scale, the much greater damage caused by the presence of the cytokine in at their storm level of activity. Taking a look at a variety of scenarios now from many different factor changes, but frankly not large factor changes, relatively modest ones. But you can see that in this plot from several different scenarios, this time span is about a month, that a lot of different circumstances can occur depending on exactly which factors are changed to different degree, from very almost zero or minimal lung damage to much more substantial amounts of long-lasting damage, but not fatal, and all the way then up to rapid, as in between 1 and 2 weeks, death from lung damage that can occur in the presence of those cytokine storms. So what's going on? I'll take you through a simple rendition of our dynamic hypothesis. The question becomes, how do you go from that initial infection to cytokine storms and death? And we'll walk through this pretty quickly. And this is obviously just an abstraction from the model diagram that you saw before, informed by some of our simulation results. So we have the initial infection. It infects some cells and begins replication to increase, and that obviously is a strong feedback loop to grow the number of virus-infected cells, and along the way begin some degree of lung damage. After a delay, and after a delay of, as I mentioned, a day or two, the system recognizes the need for a response. Various immune cells release cytokines and those in cytokines. Many of the cytokines that are released are to gear up the response of the system. So that induces the production of T cells, again after some delay. And it's those T cells that are going to be the killing agents of the virus. So this is the immune response that we want to happen. The killer T cells, and we have a variable measure of T cell strength as well. And let me just parenthetically note that the quantity and the quality of T cells varies for different people in different circumstances. And as one example, the older that you get, the less effective and the less numerous the T cells in your body are, for a few reasons. But the number of T cells and the strength of their activity kills virus-infected cells to reduce that population, and hopefully, as you saw in the first scenario, bring the virus under control. Along the way, if there is a whenever there is a deficiency of the T cell response relative to what is seen as needed, that will yield an attempt by the system to upregulate, to grow the magnitude of the response. And that's what's going on in this loop here, when even more cytokines are released to enlist more T cells to make up that deficiency and enable the T cells to effectively deal with the virus. If for any reason there is a period of time where there is a persistent T cell deficiency, this loop gets going round and round and snowballs into more and more cytokines being released, and then you're in an over response mode, leading to cytokine storm, excuse me, and much more lung damage and death. So I have to note that there, surprisingly, although the cytokine storms have been known to exist exist for a while, and occur with other disease conditions as well. In some immunocompromised situations, they're known to occur in some cases of HIV, which of course attacks T cells, and some cancers. But there's not even today an agreement on just what the real cause and even definition of a cytokine storm is, or what the causes are. But our initial analyses support the hypothesis for at least one cause, being that in the immune system's efforts to kill the virus, very severe cytokine storms can be caused if there is an inadequate T cell response. And that would cause that snowballing of cytokines trying, in effect, to enlist more T cell action and response. This was not a surprise to us. It was we thought that this could be a reason for the cytokine storms, and if the basics of this model are correct, then it certainly would contribute, if not be the primary cause. So in terms of which there's a lot of factors that appear to matter in the level of lung damage that's caused. You can see several different cases in the pace of lung damage shown in the little graph in the corner here, from rapid and highs to very high to very, very low, and really not even in the category of a storm. But the factors that matter most, and probably no surprise to many of you listening in today, involve the time delays in the system, specifically the time delay in the system's recognition of the virus, and therefore the time frame in which cytokines are released. The speed at which those cytokines respond to the virus, excuse me, the efficiency of cytokines in, I call it recruiting T cells, and then the speed at which T cells can then proliferate, which is what they're designed to do in the system when there is an antigen. And then the effectiveness of T cells in subsequently killing the virus. Because as long as the virus is there and the T cell response is not quite good enough, that is going to continue to induce higher levels of cytokines and more likely storms. So what we're hoping is that with the benefit of a lot more subject matter expertise beyond what Raafat and I possess, that further modeling work and more simulation analyses will help point toward effective medical interventions that could be used in cases where COVID gets a foothold in someone, and the disease progresses beyond any mild state. Now, interestingly, I'll just observe several of the factors you see listed on this this page here turn out to be, I mean, you have to look through a lot of scientific papers to find this observation, but several of these factors turn out to be beneficial effects of plain old vitamin D. It's, of course, exposure to the sun, of course, is the most effective source of vitamin D, which gets synthesized in people synthesize that in sunlight. Although the rule of thumb is that if you live north of, I think it's the 35th parallel, which most of us on this call do, except for Christine, I think. If you the 35th parallel runs roughly on the northern boundary of Texas, northern boundary of North Carolina in the US. But if you live north of that 35th parallel, it's pretty close to impossible for you to get sufficient vitamin D in the winter months. And so vitamin D turns out to be a useful, or it seems like, since it affects these delay times and responses, and actually prevents, it acts as an inhibitor on the overproduction of cytokines. Should be, unless you have a medical condition that makes it not a good idea. It's a pretty useful vitamin, actually a hormone, to have in your diet. So what do we want from this? We have got, in our private effort here, I think Raafat and I have gone about as far as we can with our modest medical knowledge and reading of scientific papers. And so we're hoping to get some exposure and guidance from those in the field who would understand these processes even better, and can guide and help refine the modeling work and help in conducting useful analyses, and then ultimately translate those future analysis findings into candidates for specific medical treatment. Ultimately, I think for since the vaccines seem to be very effective, but not 100% and perhaps not forever. You still have to pay attention to treatments for those cases that do break through and potentially lead to cytokine storm induced death. And certainly it would be, I've been on a bit of a crusade in the last couple of years to get more interest and work done in the field of system dynamics in this arena of biomedical, of the systems of the human body, I think are inherently feedback systems that would benefit from this manner of analysis. We'd certainly like to see more exposure in that area. So thank you for your attention. We are almost halfway through the hour, and I think Raafat and I would be happy to entertain any questions that you may have or suggestions at this point.
So I have posted a few questions on the chat. You might have seen them, or I can repeat them if you should like, but I'll appreciate it.
We do have a number of questions on the chat. I'll start reading them as on the sequence they arrive. So Thomas is asking, is there any balancing feedback loop which keeps the cytokine storm in check at all, or is it unstoppable after it is triggered?
Good question. It is not unstoppable. It is in some, for most people, the characteristics of the response of cytokines is controlled by the dealing with the virus effectively. As long as the virus is present, the system will work to try to control it. That's of course what the immune system is built to do. So if the immune system is effective through the T cell action in controlling the virus, then there's no longer the need for cytokine response. So that's one thing. And for a lot of conditions, the cytokines won't go out of control. Let me go see if I can go back. But the factors that I listed here, for people whose immune response is sufficiently rapid and effective. So for example, the effectiveness of T cells killing the virus, that's not just important for the killing of the virus. It's important for slowing the response of cytokines as well. And one of the reasons, it seems to us, one of the reasons why COVID-19 has been so devastating for people who are older. The last I saw, I think the average age of death from COVID-19 was 78 years old. I'm pretty sure that's right. One of the reasons for it affecting the elderly so much worse is that, as I think I mentioned earlier, the strength and quantity of T cells, you lose those over the course of the year of your aging. And so it gives in the simulations that we've done, a reduction in the response of T cells, which you would have if you're older, or if you have comorbidities. That's enough to trigger cytokine storms in the simulations, and so that hopefully that answered your question. It's an effective response of the immune system controls the cytokine storms.
I'm not sure, Thomas, can you say whether or not that answered your question?
Yeah, thank you very much. Thank you.
You're welcome.
So the next questions are from Professor Liz Ryder, who's in biology, if I remember correctly. It's how does
So I can just answer. I can ask them myself if you'd like. So I think mine are kind of related to what you just said, but I was wondering how the system determines there's a deficiency in the T cell response. And from what you just said, it sounds like in the model that as long as there's virus in the system, it keeps making more cytokines, which in turn create more T cells. Is that right?
Yes, that's right.
Okay. And
That's
how
right.
I'm sorry, go ahead.
No, please do.
So how does the cytokine storm in your model cause the lung damage? Is it just that if you get a certain level of cytokines, you assume there's some lung damage, or is there some mechanism in there?
Yes, it is an extremely simple formulation. There is we simply have set a factor that the higher the level of cytokines, there's a factor that just translates that into damage of a certain number of cells per unit of cytokines, or a certain percentage of the lung. So it's just a simple linear factor in this formulation.
Okay, so you're kind of basing that on what you said at the beginning, which is that we know that the cytokine storm is actually responsible for most deaths, or are you? I mean, how do you? Where did you get that number from to know?
Well, understanding that Raafat keeps reminding me that we are a work in progress. You might not be surprised to learn that number is not easily found in scientific papers. So what we did was to set a factor that that translates the level of cytokines to lung damage, such that in a typical 7 to 10 day cycle of COVID-19, that there would be in that condition a slightly higher level of cytokine damage than virus damage, and just use that behavior mode as a way of setting those factors.
Okay, but I guess my point is, what's the evidence that that's actually the case?
Oh, I mean the evidence that cytokines cause most.
Yeah, yeah, exactly.
Oh, I don't. Well, there are many sources that we came across citing that phenomenon. I don't.
Yeah, I'm not questioning the phenomenon exactly. I'm just questioning how you quantitated it. Like how, is there, and I'm not an immunologist, so I'm a biologist, but I'm not an immunologist. So I'm just wondering if there's, I was surprised when you said that cytokine storms are responsible for most deaths from COVID. That's something people are certain of. I mean, there's some evidence that's showing that, or I'm just trying to understand how strong the evidence is for your model, or whether it's just something you assumed, or
Oh, it's pretty strong. If you take a look at some of the papers describing the course of COVID-19 when it gets serious, you'll find that that's a pretty commonly cited observation.
Mm-hmm. Okay, thank you.
Sure.
So next, Professor Saeed, and then we'll go back to Thomas's questions after everyone else has a chance to ask questions. He had some more. I just wanted to give people a chance. Professor Saeed.
Thank you. I had 3 questions. I think the first one was similar to what Professor Ryder asked, the information basis for the model. And so I think that's where a domain expert can probably add value, but you must have some preliminary information basis. And I want to ask, what is it that you looked at to formulate the model? As I understand, being a modeler, what you might have assumed is that each cytokine cell will have a productivity or a kill rate for the lung cell. Is that correct?
It is, yes.
So the more the cytokines, the more the lung damage. And then the process also releases more immune system response and more cytokines. So that creates a positive feedback loop. I understand that, but I think Liz's question, what is the basis? What's the information basis for this formulation?
Sure. Well, I'm sorry, do you want me to
state all my questions? My second question was about the vaccine. Now, the vaccine enhances immune system response. So would that also enhance the probability of cytokine storms? That was my second question. Have you tested your model for response to vaccine? And my third question was, I thought that what our colleague, Professor Weathers, suggested, that there is a sort of herb-based remedy which will reduce the replication process. If that replication process is reduced, how does this affect the whole system? Have you tested that? I think all these tests are doable, and I was just asking if you have gone and performed these tests. Thank you.
Well, 3 excellent questions. Thank you, colleague. So let me address them in reverse order. In terms of the replication, the whole process of the disease progressing and the response or over response of the cytokines and the probability of a storm is reduced or eliminated by modest improvements, reduction in the viral replication rate. Probably not surprising to you as a modeler. but how is all this affected by changes in the replication? Dramatically. It's a very important factor. And Raafat, if I'm missing something in these replies, please help me out here. In terms of the question one, the information basis, a couple of things. We've been doing a fair amount of reading of scientific papers on the subject, written both before COVID and since COVID. And there's at least a partial list. When we send the file with the presentation, there's a partial list of those references appended. But I also, I have to acknowledge that a lot, excuse me, a lot of the knowledge basis comes from my work of a few years back when I was working with some very respected immunologists to build a more complete model of the human immune system. So there's some leftover knowledge still lingering in my mind from that work. And that was, as soon as I heard several months ago, the notion that cytokine storms was, the existence of cytokine storms was really or if not the primary cause of death, I started thinking about that phenomenon in terms of the system model that that I led, as I said, several years ago, and realized that one of the reasons why one of the reasons that cytokine storms are also observed in patients with HIV could, it seemed to me, perhaps be because HIV patients by definition have less effective or less quantity of T cells when the disease is not fully controlled, and that would play into the very same hypothesis that we were testing here. So those are the two primary categories of sources. And as far as the vaccine, I think we can all hope and maybe expect that the vaccine will not result in a greater likelihood of over-response. I think we can't rule it out, but because but I think it's likely that that will not happen because what the whole intent of the vaccine is to enhance the T cell response in the event of re-exposure. And as we've observed, an effective T cell response negates the likelihood of a cytokine storm.
But I haven't seen anywhere that vaccine will also inhibit cytokine storms. I mean, it enhances the immune system response, and you're saying immune system response actually gone crazy will create a cytokine storm, which is the cause of death. So if a person who has been vaccinated has an immune system response, would he be more likely to cytokine storm or less likely? That was my question.
No, okay. What I was trying to say is I believe the hope, and I think the reality is that they will be less likely to have a cytokine storm because you can't just say the immune system response and leave it at that. There's a cytokine response, and then, at least in our simple model, although I think it's basically right, the T cell response. And what the vaccine is intended to do is to prepare a T cell response that is effective upon re-exposure. And so if there is an effective T cell response, then that would reduce the likelihood of a cytokine storm.
Yeah, Ken, if you can browse up to the feedback loop that goes before that, yeah. So I think if we're saying if the T cells called for and were effective, then the loop of immune response is working with the body.
Right.
If it is less effective, then this will kick more cytokines. So I think the vaccine is improving the T cell strength or the effectiveness of the T cells to prevent the cytokines. Is that?
Well, yes, but wouldn't the risk be lower if the replication is inhibited instead of enhancing the immune system response?
As Ken mentioned, the replication rate was extremely sensitive, and it could obliterate the whole view of the model. You can just kill the model. You can just stop everything just by changing slightly the replication rate. So it looks like a strong intervention point, but there comes the place where we need the subject matter experts also knowledge. How is this controlled? And that's a place where we stopped experimenting and we're looking at other factors that create a portfolio of behavior. With the manipulation of the replication rate, it's either a kill or kill in the positive sense, like there's no infection or it's very much controlled, or it goes out of control. So it's very extremely sensitive to, and it needs this further investigation.
Thank you. I like your model. It's simple, it's understandable, and if it's verified by the domain knowledge out there, it can lead to effective interventions. Thank you.
That's certainly what we're hoping.
Okay, I'll quickly read Kareem's statement / question. I found it interesting that there is a balancing loop meant to get the T cell level up to the required level, but it can run away based on a too high limit on cytokine production.
So I didn't get the question.
Yeah, so that's related to, it's not shown anywhere in this diagram, but it's related to someone asked if there was a feedback loop to stop the production of cytokines before they got out of control. Pradesh then commented that maybe it's the delay that causes it to run out of control. What is it that's causing that to run out of control? Because there's basically a balancing feedback loop here, but it goes up and the requirement keeps going up or somehow.
Yeah, unless the response of the T cells is effective enough to slow and kill off the virus. That's the macro feedback that slows everything down is the effective T cell response, at least in this scenario. So in the absence of that effective T cell response, the system, the immune system, continues to try to increase the strength of the response. And you are right that that there are, we call them cytokines, but there are dozens of different cytokines, each of which has a somewhat different role in upregulating the response and or moderating and controlling the response. The mix of those cytokines is another factor that I think should be included in a next version of the model. And I think you're quite right that there's probably some additional balancing effect from those down-regulating cytokines. But we felt as though from the readings that the big contributor to the rapid growth of the upregulating cytokines was in effect the any degree of deficiency in the T cell response.
What I'm thinking is that if you have experimented the model in this way, there's a delay between T cells called and killer T cells. If that delay is reduced, would there be a smaller chance of cytokine storms?
Yes, short answer is yes. That is one of the delays, the delay times that is important.
So is that delay a genetic feature, or is it something which can be changed by remedial interventions, or depends on some pre-existing conditions? What controls that delay?
Yeah, I think in reality, probably there are conditions that different individuals have that change that delay from short delay and effective response to a longer delay and less effective response. One of them is certainly, as I already mentioned, one of them is certainly age. Another is the number of, and it's somewhat related to that, the number of diseases that you've already built up T cells for. Your body does not have an unlimited quantity of T cells or places for those T cells to live. And so the older you are, I guess, and the more you've been exposed to different diseases for which you have developed T cells, it's a little bit harder for the body to come up with new and effective T cells for a new condition like COVID. And I'm sure that there are some specific chemicals or nutrients or vitamins. Vitamin D is sort of the all-time great immune system helper. But as far as medical interventions, I just don't know. I don't know if there is a way to speed up that response with some sort of medical intervention, except the idea of an effective vaccine, which the whole reason for generating a T cell response with a vaccine is so that there are memory T cells sitting there waiting to respond. They don't have to be taught the new virus, right? They are there in your body waiting, and as soon as they see that same virus or one very much like it, they're ready to go to work. And that the memory T cell component, I would suggest has the effect of reducing that delay that you correctly point to as very important.
Well, wouldn't that reduce actually the delay between virus infected cells and cytokine release? I mean, if wouldn't the vaccine reduce that delay instead of this delay between T cells called and killer T cells?
I'm sorry, I don't think I heard all the question.
That if the vaccines create cells with a memory, that might reduce the delay between virus infected cells and cytokine release.
I don't know if that's the case. I just don't know if it reduces that delay.
The ability of the body to discover that there is an infection, which is the interferon response delay, I think you're referring to.
Right. I don't know if the detection of the presence of a virus is speeded by the presence of by a vaccine. I wouldn't be shocked, but I know that the presence of memory T cells that get generated by either having the disease or by an mRNA vaccine. I know that the speed of response from the killer T cells is faster in the presence if you have memory T cells sitting there waiting. They don't have to go through a days of proliferation and expansion. They're already there. So that I think would effectively reduce, you could call that a reduction in the delay of the response of T cells.
Perhaps in terms of the model, it will be helpful to test the sensitivity of both types of delays if you're addressing the vaccine response. And I think this is very interesting that in this simple model, one can see that replication plays a key role, and any remedial intervention which affects replication can be very effective.
Right. It is, and the balance between the replication rate and these time delays in the response of at different points in the response of the system is a really crucial set of trade-offs.
I think Professor Brothers, our colleague, Pam, might be interested in this model, especially there's a mechanism there which sort of reinforces the remedial intervention that she has identified.
We would be delighted to follow up with someone who's more familiar with the science of all the processes.
Thank you. And I would like to point out we're at the top of the hour, so if people have another meeting, please feel free to leave. We're actually 1 minute past the hour now, and I have a few minutes if people would like to continue to stay, but please don't feel pressured to do so.
Well, before we lose everyone, I just want to thank on behalf of Raafat and myself, the chance to talk about this. It's something that's very near and dear to us in having a chance to talk with colleagues and some experts is really appreciated.
And we will, this work or another version of the work will be presented at the System Dynamics Conference in July. I think it would be in one of the poster sessions. So feel free to stop by and maybe see more progress and give us more feedback there. Thank you.
Can you make the model available to people to experiment with?
No, let us. Right now, it's really not in a very friendly state, but let us try to figure that one out.
So
I think that's just what we would like to have happen.
Christine, are you going to over any other questions or?
The other question, the person is gone, I believe. So I can ask. So Hannah made a comment, wonder whether there is anything to be learned in looking at literature on the 1919 flu pandemic, in which younger people with stronger immune systems were more likely to die because of something triggered by overactive immune response. Is there a link to cytokines, which in this case appear to be controlled by the immune response?
That is really an excellent observation. I think neither Raafat nor I have seen scientific papers that refer to cytokine storms in the 1918 epidemic. That's not to say that it didn't happen, but in the readings that we've done so far, we have not seen reference to cytokine storms.
And all the other questions were addressed in Kareem's question about the balancing. I think that's it, unless I missed something.
Yeah, that's great. Well, again, thanks to everybody.
Thomas had a couple of questions, I guess.
Yes, I just kept seeing about feedback loop, which creates a benefit for the virus from escalating the cytokine level. That was similar to what, yeah.
Yeah, I think it's the delay. We probably covered that. So if the delay is reduced, in fact, there'll be less likelihood of a storm. So thank you. Very interesting. Keep up the good work, folks.
Thank you. Maurice has a comment or question at the very end.
Yes. So I'll just read it, I guess. I'm interested in finding examples of medical phenomena that can help medical students connect to the methodology. Do you think this could be an effective example to train medical students in system dynamics?
But that is a great observation. I think it's fantastic. The use of simulators in education is long since proved to be extremely effective, as you know. Let me just plug in a little bit here. While I move my camera a bit. I have spoken with a couple of deans of medical schools. I just told this story to Raafat yesterday. So sadly, there, based on my limited sample, it appears that there's very little in conventional schools of medicine, very little attention paid to how the immune system works. I found that shocking, frankly. But one dean specifically said to me when I asked him about that very question. He said, well, we really, we consider ourselves fortunate if our graduates know what the main actors in the immune system are. We don't even attempt to teach them how the whole system works. And I was just floored by that comment. But hopefully there are medical schools that are more thoughtful about that. And I think the idea of using simulators of this sort or any other systems of the body, especially models of the immune system, would be a tremendous teaching and learning aid. I don't know, I'd be interested in hearing what the rest of you think about that idea as well.
I'd like to add a positive note. Jim Rogers and Ed Gallagher worked at Mayo Clinic, and it was a system dynamics model on treatment of a different condition, which, as I recall, what was it?
It was the kidneys.
Yes, yes. And they were able to implement their model and test it on patients. And actually, Mayo Clinic is still using it to create specialized medications for patients. So I think there's a great opportunity out there, and particularly a medical student can be a bridge to connect the two domains.
Good point.
Yeah, Jim Rogers. Yeah, Maurice, want to speak to you guys, to us? Yeah.
Yes, please feel free to unmute if you mean right now. I wasn't so sure if you mean right now or in the future.
Now is good. Now is good.
Yes.
First,
Maurice, how are you doing?
greetings to Ken. Long time. I think we haven't seen each other in 3 or 4 years. So a really fascinating presentation. I'm really sorry I had a conflict and managed to miss most of your presentation. So I'm just gutted about that because it looks fascinating.
But I think it's being recorded, so it will be accessible in some way that I don't know about. But
okay. Well, last week I was contacted by a professor in India who is interested in training their medical students to do epidemiological modeling. And as you suggested, Ken, it is surprising how little training the medical students get. They don't seem to have any skills in this area. Partly that's a function of siloed responsibilities in the medical school because there's an epidemiology department and there's a XYZ other departments, and the medical students don't get the epidemiology. We've developed some courses for epidemiology modeling the pandemic, and they're interested in using these. But I thought it would be to connect with the medical students. I was looking for examples that would they would relate to, and they're in the middle of a completely tragic situation in India, surrounded by cytokine storms everywhere.
right.
So this is hugely relevant to them right now, and I thought it would be a fantastic thing to show them as a way of engaging them. So that's why I was so interested in what you've done, and I think it's really important. So anyway, that's the background. What do you think? I mean, do you think this could be a is it too complex to as an introductory way to get medical students engaged, or is it at the right sort of level?
Well, you surprised me, Maurice. When you started that question at the end, I thought you were going to say, "Is this too simplistic?" But the question was, "Is it too complex?" Again, I am just I am a huge fan and proponent of trying to get this manner of thinking and analysis into medical training. So if there's a path that you see to get this this specific relatively simple model in front of medical students as a to help them start thinking this way or gain some insights, we would fully support that.
Would you be willing to give a short presentation to the class if we get this going? It's probably happening next couple of weeks.
Yes is the short answer. I think Raafat and I would both be happy to do that if the schedule can be worked out.
All right.
Yes.
Well, let me. I think your emails are both on the announcement, so I'll just jot you a quick email describing the situation a bit more, and you can. And I still need to check with the professor. This is at Delhi University of Delhi Medical School, to see how she wants to do it. But they're quite keen to try and figure this stuff out, and bizarrely they don't have the skills. So I think this would be a fascinating way to help them connect to it. So yeah, let me jot you an email and explain what's going on and see if there's an opportunity.
That'd be great. Great idea. Thanks, Maurice.
Yeah, it's great to see you too. Looks like you're getting you're being exposed to some good weather. That's nice to see.
Occasionally.
Yeah. Well,
where are you geographically?
In London at the moment, and we'll be here for next couple of weeks at least, and then hopefully in a place with good weather down in Greece. But not heading to India anytime soon. That's it's a really tough situation there at the moment. We have a group of students there that we've been working with, and that's how this opportunity arose.
Students in system dynamics.
Well, yes. I mean, we have some courses. I'll send you a link to the initiative we've been running. It's we're going to present we have a presentation scheduled for the System Dynamics conference in July, but I can send you a copy of that so you can see it.
Yeah, super. Thanks.
It's basically teaching teenagers how to do epidemiological modeling, and we've had some good results from that. And this group in India has been really fantastic. So we're that they've written some articles and really done a great job. And the reason the university contacted us is because of their articles. So
that's great. Your observation earlier about the silos in not just medical schools but medicine in general brought to mind another comment that seemed shocking to me at the time, a few years back, when the lead immunologist that we were working with back then, in the course of explaining some of the workings of the system to us while we were designing the model back then, observed that the same observation about silos, and she said to us that the T cell people don't really talk to the antibody people, and the B cell people don't really talk to the T cell people, and it just boggled my mind that something called the immune system was not studied as a system. So, and I think that's largely still the case.
Well, in that case, what you've done here is a breakthrough, and congratulations. It looks really great. You know, I think it'd be really amazing if we could somehow, you know, incorporate or complement, I should say, what we're doing with what you've done here.
Yeah, great. I might even overload you with another piece or two as well, Maurice.
Thank you so much. I'll just put my email in the chat if you want to.
Yeah, that's great. I'm not seeing the chat, but I know that Christine or Raafat will have it.
Yes, Christine is keeping everything.
Okay.
Yes.
Well, thanks for tolerating my late my late arrival and my questions. Really appreciate this.
Thank you, Maurice. You made a big difference, huge difference actually, with your comments and the opportunities.
Well, I really appreciate it. I'm just sorry I missed the whole presentation, but I'll look at the recording when it gets put up.
Yeah, and we'll make a PDF available as well.
Okay, thanks. I'll just grab my email, or I'll pick up your emails off of the announcement and duplicate it there just in case. But thanks very much. And it's great to see you, Ken. You're looking well.
Thank you.
I continue to age.
Yeah, well, so do I. I think that's inevitable, right?
That's my objective right now, is to continue aging.
Aging well too.
Good. Best of luck for continued aging.
All of us actually.
Yeah, we're fighting an interesting enemy at the moment. So thanks very much.
Thank you.
Our pleasure.
So I think there's only one question that I'm not so sure if you did answer, because I have a bad memory, but I'll ask it in case you want to answer verbally. So Thomas asked this: apparently early detection of an excessive cytokine level increase is crucial. This could be treated, but the question is there a leading indicator which can inform about an emerging cytokine storm?
You know, I don't know the answer to that question. I'm not. I just don't know. That's a level of medical scientific knowledge that I don't have. Most of the things that we've analyzed here I think you would have to consider to be in the form of preventative measures rather than a real-time response, where a leading indicator would be valuable if there was some manner of monitoring that leading indicator, and once identified, a rapid intervention. I think most the things that it's a great question. The things that we've tested so far are what if you could have a more rapid recognition of the virus early on by those cells releasing cytokines, but we haven't tested anything. That's an interesting idea. We haven't tested anything where once the process starts, testing some kind of intervention. I don't know what those interventions would be medically, but certainly the idea of testing to see what the opportunities would be at different times. Raafat, we should do that. That's a good idea.
Yeah. I'm writing this note specifically.
Yes, unfortunately, Thomas left, and I wanted to give other people a chance to ask questions, so I didn't ask all of his questions until now, I guess. I think that's it.
Yeah, thank you for asking the question, Christine.
Yes. And when I post the video, I'll also post the PDF that you will share with me.
Good. Yeah, we've been as we were talking about beforehand, finding little bits of things that we wanted to fix, like arrows that were not straight and all that sort of thing. Right up until, what was it, last night, Raafat, when we exchanged our last small fix. So we'll get that in the email to you very soon, Christine.
Thank you. And are there any other last comments or thoughts? And I would like to thank you for presenting. Everyone else has been saying thank you a lot in the chat and verbally. But yes,
Great.
thanks.
Thank you.
Our pleasure. Thanks for the opportunity.
Thank you.
No last questions. And I'm going to formally stop the recording and end this meeting.
Thank you.
Thank you again.